Hello, everybody. This is the next part of our Prague mathematical physics seminar. And today we are very happy. We can welcome Ruggero Noris with his talk about supergravity viewed as a gauge theory with the subtitle The Geometric Approach. Ruggero came to us from the Central European Institute for Cosmology and Fundamental Physics in Prague. So this topic is very interesting, I hope, for all of us. And that's the point where I would like to stop and
thank you.
Give you the floor.
Thank you very much for the generous introduction. Yeah, I'm really happy to present this topic. I hope that I will be able to convey some of the interest that I have in this topic. So let me start by just pointing out some reviews, some references for this topic. So the first is the book by Castellani, Darren, and Fred. In particular, the volume 1 and 2 are those that one needs to have a complete grasp of the technical aspect of this approach. Then there is a very nice review by Castellani, and I also added these two papers, which are some recent applications of such an approach to supergravity. So the aim is indeed to review the geometric approach, to study, to review the strengths of this approach, and maybe to give a hint of its mathematical subtleties. So we'll start by talking about historical motivation. Then I will move on and talk about the mathematics, so the technical aspects of this approach. I will then discuss an example, which is n equals 1, d equals 4 supergravity, and I will conclude with some comments on possible extension of such an approach. So, let's start with the historical motivation. So we know that gauge theories are well understood in the mathematical from the mathematical point of view. Indeed, they are constructed in terms of principal bundles. We can study and we can take the connections on them, and these connections are the physical fields that appear in these theories. One can study, for example, also particles that couple to such physical fields, and then one studies associated principal bundles. So, for example, we can take the Maxwell theory, which is just take the principal bundle with U1, and we have a connection A, and its strength is F, and the action is just given by in this way. So this is integrated from the math. Right.
May I ask you for
Sure.
writing bigger letters because of the bad quality of the stream?
I will definitely try to do it.
Thanks.
Okay. In this context, the quantum properties of such a theory, so of these theories can be studied in terms of the path integral, which is a formal integral on all the possible configurations of the field, weighted by an exponential of the action. So due to the success of these theories, it was natural to try and formulate supergravity, which was a theory combining both gravity and other interactions which were formulated as gauge theories in a single theory in a similar fashion. So this is the main idea of supergravity, to study gravity and supergravity as a gauge theory. So in this sense, we want the symmetries of the theory to be coming out from group theory, as in gauge theories. This formulation had a huge success throughout history. For example, I can cite you the paper Varia, 1982. It has this approach has had a huge success because of its algorithmic nature. So there is an algorithm that allows you to construct every theory. And in this paper that I'm citing now, the authors managed to study not only the theory but also the symmetries behind the 11-dimensional supergravity, which is thought to be the lower energy effective theory of the M theory, which is sort of generalization of string theories, superstring theories. So, despite this success from a historical point of view, I believe that a proper and rigorous mathematical explanation of such an approach is still lacking from the literature, and I would like to, in this seminar, to try and outline these mathematical holes. Okay, so the first step in order to construct the theories is the choice of an algebra, of the algebra.
Sorry, can I
Sure.
ask like a devil's advocate question?
Sure.
So it's not completely clear to me what is better understood about H theories than gravity, which would kind of
quantization
suggest.
Quantization mainly.
I don't think I agree. I mean, they both quantize the same.
Yeah, but for example, gravity is non-renormalizable from this point of view.
So are you saying that one of the hopes of this program is to come up with a renormalizable gravitational theory?
Well, at the time when this was proposed, I would say yes.
Okay, but now we know that doesn't work, right?
We know that this doesn't work,
so,
but it is still a very powerful tool to construct supergravity theories. Okay, so now,
yeah, I'm trying to understand what you mean.
But... since this yields an algorithmic procedure in order to build Lagrangians, for example, which determine the dynamics of fields, and since this is an algorithmic procedure, I think this is an interesting way in which to study supergravity. In this approach, the symmetries of the theory come out in a more natural way, I would say. For example, supersymmetries will be understood as super diffeomorphism of a supermanifold. If you study instead supersymmetry from a space-time point of view, it's kind of more subtle. What's the geometric meaning of the symmetry? So this approach is, the idea is that symmetries comes out from group theory.
Okay, but just to follow up a little bit, suppose that you already have your favorite supergravity theory, right? You don't need to build a supergravity. You have your supergravity theory.
Okay.
After this point, do you see any advantage of treating it as gauge theory?
Well, not in the original approach as it was proposed 50 years ago.
Okay.
Almost 50 years ago. This is a way of understanding, a different way of understanding supergravity, and it's useful to construct these theories. But I think that, for example, there are a lot of points where this where new knowledge about supergravity itself could come out, for example, from superspace itself, and Carlo, for example, is an expert on this. So I think that now, in the late 70s, they had different purposes. Okay. Now I think that where this approach really shines would be as a superspace approach. This is our state its main strengths. Okay, but still, I think that something is lacking from a mathematical point of view, even in the approach of the 70s. Okay, this is what I'm going to discuss. I hope that will be exhaustive enough.
Okay.
Okay.
As always, we hope to expect some interesting math.
Oh, man. We'll see. Okay.
Why we do physics?
Okay, so let us start with Lie algebra. I'm going to denote this Lie algebra with in this case with G. And for the cases of interest, this algebra must be chosen in such a way that it's split in this way. So H will, as a vector space, H will contain generators of the gauge symmetries like Lorentz or some internal other symmetry of our theory, for example, the R symmetry of supergravity theories. I will be related to translations, and O will be related to supersymmetries. So this part of this supervector space, these are the fermionic generators. So the algebra has to satisfy the following relations. I hope that this is clear enough. Okay, so let's comment on this. This is a subalgebra. This means that H acting on I and O as vector spaces is a representation. Then we have that I with I is just H, and finally then O with O is H plus I. So this is the a graded commutator, as you can see, because these are fermionic generators, and this is what the main feature of supersymmetries. So two supersymmetries close on translations. As examples of such these algebras are, for example, super Poincaré, the orthosymplectic algebra, the D2 and alpha algebra.
So these algebras like this should be a super algebra.
Yes, yes, because these are fermionic generators. Okay, so if you prefer, I could have written.
No.
Okay, okay. So this algebra is spanned by this the generators TA. We call them TA, where A goes from 1 to the dimension of the algebra. The dual space is spanned by sigmas, so these are left invariant one forms, and these satisfy the sigma A TB. And in particular, these sigmas satisfy the Mohr-Krapin equation. Okay, so these are the structure constants of the algebra. And in particular, the Jacobi identities defined by the structure constants are the same thing as d squared. So they are the same thing as the nilpotency of this operator. Okay, this setup is not enough to study gravity theories because the metric that one obtains from group theory, which is the Cartan-Killing metric, which is just written in terms of the structure constants. It's just a constant, it's fixed. So in order to introduce dynamics, which is what gravity is all about, we need to deform this setup. So
I'm very ignorant about this stuff. So can you tell me what is the differential bit? What is the differential calculus here?
okay, so this is an algebraic D. This is not the round differential. So this is just a standard way of defining the dual of the algebra. If you want to see this, you can contract this equation with TA and TB. Okay, and you will see that exactly this relation comes out.
But you can think about sigma as invariant
Yes, these
long
are
forms.
yes, these are
And
invariant.
then we just do
Then
and it's that. Okay. Ah,
If you want to think about the group, this group theory, this group, you can think of it as a group, a principal bundle over a single point. So yeah, the group and a single point.
okay.
Okay, so this is not enough, and indeed we need some sort of generalization or deformation of this setup. This is fine. So this is why we introduce soft group manifolds. This is, yes, in quote definition. So these are, they will be noted by this G tilde. These are characterized not by these sigmas, but from these one forms, which I will call mu, and these mu are not left invariant, and these these do not satisfy the Moore-Petan equation, but indeed they satisfy this equation. Okay, so this will not be zero, and whatever it is, it's called R. Now, once we have this, we can apply the differential operator, and we obtain these relations. So this implies okay. We'll return on the interpretation of this equation shortly. So now that we have these mu's, we can look for the duals, the dual vectors of these one forms, and these will be called T tilde, such a way that this yields a delta. And from this definition of the T tilde, once we apply, once we consider this equation on two of these T tilde, we obtain that they do satisfy an algebra, but it's not a Lie algebra anymore. Okay, so because of this term, this is no longer an algebra. This is rather a structure function. These are rather structure functions. Okay, so once we have these vectors, we can consider a vector field and study the transformation laws of these mu's. These mu's will be the physical fields of our theory. So it's nice to study their transformation properties under such a transformation. So we choose epsilon is plus epsilon a T tilde a. And the transformation of the field is just the Lie derivative and field. These mu's are forms. I can rewrite this like this. So this is A plus. Now I can add and subtract 1/2. Okay, so I will call this variant derivative lambda of epsilon A. Okay, so we see that whenever this is 0, the transformation law of the field is just as a gauge transformation. So we can think of electromagnetism. We have the transformation law of A is just d lambda. Okay. So this leads to the concept of horizontality. So we can actually ask for the subalgebra H to remain a symmetry of theory by requiring that the contraction along the vector H of R is 0. Same as saying that R A H B is 0. It's the same as asking that the tilde H satisfy the algebra. This is just okay. This requirement actually splits the G tilde in a principal bundle structure, which this is where this is the total space. G tilde over H is the base space. H is the fiber, and then we have projection. Okay. In this sense, every mu, every field locally, which is locally a function of x and h. So these are the coordinates on the basis, and these are the coordinates on the fiber, is written in terms of mu x 0. So the base space is immersed into the total space by just performing H transformations. So there is, of course, there could be an alternative derivation of this approach, which, however, I think it fails on some aspects. So let me see if I can explain this to you. So the problem with the definition of this soft group manifold is that the definition indeed the definition itself is indirect. There is no mention on what kind of deformations one is actually studying and choosing, and so a better way, I think, to understand this is to consider instead principal bundles. So in principal bundles, one can choose a connection, a principal connection, which can be written in this way, and this is locally can be written in the following way. So join. Okay, so this is these are the left invariant forms on the group. This is the joint representation of the group on the algebra, and this coefficient only depend on x because this is, as I told you, a principal connection. And once we define this, we can define also the curvature of such a connection, which is just the exterior derivative of the connection, and it's written as in the following way. So. Okay, so you see that this is precisely the same definition of curvature that I used before in the soft group manifold, and moreover, this is the differential on the principal bundle. This curvature satisfies exactly the same Bianchi identities that I wrote before. Furthermore, they are horizontal, so we don't have to implement it by force. So R of V dot equals 0 if V is in the vertical space of the principal bundle. So the advantage of using this approach is that global issues, so globality and locality is better understood. So all these aspects that I didn't mention, mention before. But the disadvantages are that now for any vector field, the transformation laws of the field are just, so there is no contraction here. Yeah, before there was, so this is not there. And this is not what we want for gravitational theories. So one way to understand this is the main difference between gravity and gauge theories. And this is due to the fact that translations and supersymmetries are not vertical transformation, they are on superspace, so they are horizontal in this sense. So a way to solve this problem, this approach would be to find some sort of identification between these vertical directions and these vectors, these horizontal vectors. This quotient procedure has not been understood completely, but it yields correct results. For example, for the GR case, in GR we can take principal bundle with SO31, so comparable. And so the dual of I is the field line, the dual of H is the spin connection. And to identify I with d mu is the same thing as saying that dA is actually dA mu dx mu. And furthermore, this identification yields the known and correct transformation rules for all the fields. So to understand this, how this quotient procedure is performed would mean to understand how we can avoid using soft group manifold and work instead with the principal bundles. So let us go back to the approach. And let me introduce the concept of rheonomic. This is the main concept in supergravity theories. So we said that we have this kind of structure. This is a supermanifold. So locally it is described in terms of coordinates, which are x, mu, and theta alpha, for example. Okay, but this theta alpha are anti-commuting variables. So theta alpha, theta beta equals minus theta beta, theta alpha. And most importantly, we have no reason to believe that this Colony actually exists in nature. We have no phenomenological proof of their existence. So it is fair to assume that all physical information should be contained in space-time, which is the slice theta equals b theta equals 0. Okay, so this is the assumption. This is what characterizes this approach. There may be, of course, other embeddings of the bosonic slice into superspace. This goes beyond the scope of this seminar, so I'm going to forget about this. And Carol is an expert in this, so next time he can talk about this. This constraint actually implies that mu a as a function of theta and of x and theta actually depends only on mu a component rho x0 dx rho. Okay, so this translates into this requirement. So let us see what happens if we perform a supersymmetric transformation of this vector, of this one form. So mu a x d theta is mu a x0 plus the lead derivative. Okay, now we have the expression of this lead derivative. It's mu a x0 plus 2 times epsilon alpha r a alpha and x. Okay, the way to understand this relation is that it can be shown that these terms, which are evaluated at x and 0, are actually it can be proven that these terms are proportional to the derivative of mu. Okay, these are proportional to this term. So it seems that the mu at x and theta depend on the correct information, so mu a, but they also depend on these normal derivatives. So the way to remove this dependence is the following. So as I was saying, the way to remove the dependence on d over d theta of mu is to impose that r a alpha m is c Okay, so what we are saying is that the components along the supersymmetric directions are proportional in an algebraic way. So these are constants to the components of the curvatures along space-time. Okay, this is just the mu a mu plus c. Okay. So you see that by imposing this, we are actually removing the dependence on the derivative of mu, and it all depends. The Cauchy data required for this mu reduces only to the dependence of mu rho 0. Okay, so this is the only thing that it is necessary to know.
May I have a question? How do we derive this equality? Or
this is not a derivation. We impose. So this rheonomic constraint is a physical constraint. We are saying there is too much information on the whole space. All the information we want is on a slice of. So we have to impose that all the information is contained here, and the way to do it is to impose this. Okay.
This is the rheonomic condition.
Yes, exactly. It comes from Greek. It means that the information flows from space, from space-time into the whole superspace. They decided to call it like this. Okay. In presence of these constraints, the Bianchi identities satisfied by the curvatures actually become satisfied. They become satisfied. They become constraints. So themselves. So this implies that there are some relations between these coefficients that allow to satisfy the Bianchi identities, and these relations between these coefficients are precisely the equations of motion. So we see that we know that Bianchi identities and the squared are the same thing. But we also discovered that there are some relations between these coefficients, which I will call equations of motion, that allow to satisfy the Bianchi. And from this, we know that the Lie derivative closed in algebra Okay, so in the case of supersymmetries, so if these are supersymmetries, we are actually saying that if the equations of motion are true, then the supersymmetries close an algebra. So this is a known fact that supersymmetries are only closed on shell. Okay, now we can finally go on and talk about Lagrangians. Okay, so Lagrangians can be built according to 5 principles. So the Lagrangian, the first principle is geometricity. So Lagrangian must only contain this mu A, wedges, the differential, and possibly zero forms. Furthermore, the Lagrangian must be integrated only on the base space as a submanifold of the soft group manifold. To perform such an integral, of course, one would need the Poincare dual, and in presence of supersymmetries, this Poincare dual can be obtained in terms of integral forms and picture-changing operators, which are again beyond of the scope of this seminar. I don't have time to cover them, but we can leave the embedding of the base space into the total space unspecified at the price of not using the Hodge dual. So we cannot use the Hodge dual, and in most cases this is not a problem. So we can avoid this by using Lagrange multipliers to enforce on shell this constraint. So in principle, this Lagrangian contains the same information. This is a superspace Lagrangian, and it contains the same information as the Lagrangian on spacetime. So why bother doing so if this yields the same information? Well, it's even harder to build actually. The point is that understanding this, it allows to express all the symmetries in a more geometric way. So all the symmetries actually come from the group that was chosen from the algebra that was chosen in the beginning. So the other another principle that one has to follow is the H invariance. Okay, so every the Lagrangian must be built in terms of H invariant tensors. There cannot be like free connections, like there cannot be free spin connection. The spin connection, for example, can only appear inside its curvature. Another is the scaling law. Every term in the Lagrangian must have the same scaling as the Hilbert-Tyson term, and the Lagrangian itself, every term must be must scale in the same way under the rigid rescalings of G. As an example, we can take H, I, and I, 0. So you see that if H goes into H and I goes to WI, the algebra remains the same. And this is the same thing as saying that spin connection. This is just a Poincare group. So this is just general relativity, standard general relativity. So if one performs this scaling, every term must scale in the same way. Then we have other two principles. So
sorry, what's the W?
just a parameter, a constant. I'm just, if I'm saying rescale every term here, every term I, there will be a W here and W here. This is 0, so there is no problem. Okay. Since this is invariant under rescaling, we want the Lagrangian every term to have the same scaling as the algebra. Okay. This is another requirement. The vacuum existence. So the equations of motion must allow the condition, the solution RA equals 0, which was the one defining the rigid Lie group. Finally, rheonomic. On shell, so when the equations of motion are valid, the curvature, the outer components of the curvatures must be expressed in terms of the inner ones. Let me see if I. Okay, this must be true. Okay, so now I can finally go on and talk about an example. This will be sort of a list of formulas, but I will follow the exact points that I outlined here, and these results can actually be obtained by just following this algorithmic procedure. So take n equals 1, d equals 4 subgraph. So take the super algebra, the super Poincare algebra. This is just H that goes, the H and H that goes into H, and we have H and I that goes into I. Then we have H and O that are with generators will be called Q that goes into O. Then we have P with P 0 and Q with Q that goes into H plus I. In this case, there is only I. Okay, so these are the gamma matrices. They satisfy the Clifford algebra. So A, B, 2, B, B. This is the antisymmetric product of the gamma. This is the charge conjugation matrix. It satisfies the following relation. And these are Majorana spinors. So these are real spinors. They satisfy the relation that QAC alpha beta equals Q dagger alpha gamma 0 alpha beta. And this will be denoted as Q bar. So again, we chose an algebra, now soft forms. These are mu A, omega AB, VA, and psi alpha. And these will be dual to some tilde vector. So mu A B tilde B is LP. And these satisfy following relations. So it's B minus omega. So these are the curvatures. Yankee identities can be derived by applying the operator. So these are okay. So this is the Bianchi identity related to RA. Then the one related to RAB is the RAB. And finally, there is the one related to RO. Okay, these are the Bianchi identities. So we know that these identities will become actually satisfied in terms of constraints, and these constraints will be implied by this rheonomic constraint that imposed here. So the parameterization of the curvature is the following. Okay, here there is 0, so there are no other components along the vector psi v or psi psi. So these are not there. But in this case, there is one term. And in rho is again only the VV component. Okay, we understood that the components of each curvature along the supersymmetric directions must be expressed in terms of the inner components. So only on this set of curvatures. And indeed, it is the case. If we substitute this expression into the Bianchi identities, one obtains that this is proportional to rho AB, this one. And furthermore, as I said, these equations will be satisfied only if rho A, B, C, sorry, R, A, B, C is 0, if R, A, C, B, C minus 1/2. Okay, so these are the Bianchi identities will be satisfied only if R, A, B, C, so the torsion is 0. This can be recognized as the Einstein equations, and this is the Narita-Schwinger equation. So we see that the information, the equations of motion of the theory are already are the combination of the Bianchi identities and these constraints.
You were Supergravity term comes from the rheonomic constraint.
Yes.
Why is there a term depending on psi and v?
Okay. In general, I could put something, for example, I could have also something side side there. But if you do, you with some coefficient, you try and plug in these expressions into the Bianchi identities, and you see that these components cannot be there. Okay. Furthermore, since this has to be expressed in terms of this, in terms of one of these components, this was the rheonomic constraint. You can find, I have the explicit formula that doesn't have anything in this case. If you do that, you find that this theta is not a general function of all the 3 components, but only of this. Okay. In other cases, it may happen, however, that all of them contribute. Okay.
Just also
Sure.
a question. I'm not sure I understand the content of the rheonomic condition. Yeah.
I can.
So I mean, there you wrote what your field content is, right? So these are omega, v, and psi. Is that correct?
Yes.
Okay, and then so the R, rho are definitions.
These are, yes.
Yeah.
These are just, you remember when we defined soft group manifolds, we said that this is no longer 0. These are not Morin-Cartan equations. This is equal to something which I call R.
But these equations are just definitions for these R and rho.
Yes.
Okay.
Yes.
And then the Bianchi identities
Follow.
are tautological.
Yes.
Once you have the definition.
Yes.
Okay. So now the rheonomic condition, the general one you stated involves some of these constants. So some the general curvatures
Yes.
expressed in terms of components that when v and psi is 0.
Okay.
So what these C constant or C coefficients, how are they determined? Are you determining
Exactly by substituting this expression into the Bianchi identities. Okay. If we don't say, if this coefficient is left, it's not proportional to this, then there will be no no longer any constraint.
So if there was no rheonomic constraint,
Exactly.
you could take these R's and
Exactly.
rows that you define and expand them in basically as polynomials and VM psi.
Exactly.
And then only some values for the coefficients are admissible.
Exactly. And yes, and this is precisely expressed in terms of this with a suitable coefficient, which I before called C, but I can write you this expression, but it's just etas and so on.
So is the claim here that the formula that you wrote here is the most general form of these curvatures consistent with the rheonomic?
Yes.
Okay.
Okay. Yes. Yes, it is. If you want to try out things here, they will not. You will obtain inconsistencies with the Bianchi identities. Okay. And not only that we obtain this, we have this with specific coefficients that can be determined through the Bianchi identities. We also obtain relations between the space-time components. And these are exactly the equations of motion. Okay, so we can move on and talk about Lagrangian. So, almost over. So the A, B, and C points rules that I was stating before allow to obtain Lagrangian in this way, in this form. Okay. So the existence of the vacuum, so the D condition, actually fixes A 4. So this is the complete n equals 4, n equals 1, t equals 4 supergravity action. And the equations of motion indeed are can be derived, and indeed are C, T, A, B, C, D, 0, which is actually 0 when R is 0. Which is the condition, the vacuum existence condition. Again, if rho and R are 0, this is 0. And then finally, again, if R and rho are 0, these are 0. Okay. So let me end with some content, with some comments on this approach. In this approach, we one of the rules for the construction of Lagrangian is the use of one forms. So what if we want to construct Lagrangians or dynamical theories for scalars, for zero forms, both bosonic or fermionic, or for p forms? Well, then in that case, for zero forms, it is somewhat easy. Indeed, one can take a representation, and when one has a connection on the principal bundle, one can study the covariant derivatives on the associated bundles. So once we have a mu, we have on the associated bundle a covariant derivative, which is just b plus mu a d a. So we can use this d to define some sort of curvature of, for example, a scalar field, which is a zero form, bosonic zero form. And this, as the curvatures, will be expressed in terms of, this will be a one form, so it will be expressed in terms of a field line, and in terms of psi. And by the rheonomic constraint, this will be expressed. This has to be expressed in terms of the inner components. Furthermore, we know that when we have a covariant derivative, the square of nabla is proportional to r, to the curvature. So again, here we will need the rheonomic parametrization of the curvature, and everything else follows. So the construction of Lagrangian, the study of the symmetries is the same. So for p-forms, in the situation is a bit it's a bit harder. Indeed, one has to study to find Chevalier-Heilenberg cohomology classes, and one can associate to them p-forms or fields, new degrees of freedom. Finally, the last thing that I would like to mention is the possibility of construct supergravity Lagrangians in which the supersymmetry holds off-shell. This is the problem of the auxiliary fields. This has been understood in this approach, in this concept, in this approach, in a very limited amount of cases. For example, in d equals 4, n equals 1 supergravity, this has been understood in the rheonomic approach, in this geometric approach. But in more general cases, we have no clue on how to build it. And this is precisely what it is, a work in progress. And this is precisely what I'm working on with Carlo and a group in Torino. So that's it. I hope I was able to give a hint with 1 hour of time to give you a hint of this approach, and I hope it will be of some interest. And if you have questions, just ask me.
Thanks very much for your nice talk. So,
Can you introduce also higher forms?
Like p-forms.
Yes, p-forms.
Yes, as I was saying, yes, it is possible. To do that, you need to find there is a construction method which is based on Chevalier-Heilenberg cohomology classes. So whenever we have a cohomology class, so we have an object made of mu's. So let's call it omega. Okay, this object is, for example, a 2-form, a 3-form. Okay, so this is a 3-form, and it's closed. Okay, but it's not exact. And then one can associate like a term, so we can add to those mu's. We can add an a. I just call it a plus omega 3. Okay, and this I will call it r. Okay, so we added 2 forms whenever for any cohomology class. This is the way. This generalizes the starting Lie algebra to what is known as the free differential algebra, and this is related to L-infinity algebras. Okay, so this is the way to do it, and it is pretty hard to find cocycles, but it's a possibility. For example, the d equals 11 supergravity. So the 11-dimensional supergravity contains a 3-form and a 6-form, and these are built exactly in this method, in this way.
And then you use the same rules.
Yes, precisely. Yes.
I assume it works also with covariant.
For the yes, this is exactly what I was saying here. You define this to be some sort of curvature of this field. They call it curvature, but of course it is not a connection. But in any case, you impose that these coefficients along the outer direction, the fermionic direction, must be expressed in terms of the inner ones, and then everything follows. One of the references that I gave you in the beginning precisely does this for an hypermultiplet. So for a theory with a scalar and spin 1/2 fermion. So it may be interesting if you have doubts on how it works.
Maybe I would have a question. Is there somehow important to have a Majorana representation?
Okay. In this case, yes. The conditions on spinners are chosen in such a way that on shell, so when the equations of motion are valid, you have a matching of degrees of freedom. Okay, the supersymmetry is exactly this. A matching of degrees of freedom on shell. So if you were not to impose Majorana, the Majorana condition, you would have twice as much fermions. So on shell, instead of having 2 bosonic degrees of freedom from the metric and 2 fermionic degrees of freedom from the gravitino, from the psi, you would have 4. So you would have a mismatch. For example, in 6 dimensions, you impose different conditions. They are called like pseudo-Majorana.
Is the existence of such a representation guaranteed?
No, the existence of like Weil fermions or Majorana depends on the dimension. For example, in 2 and 10 dimensions, you have Majorana Weil spinners. But there is a whole it changes, it varies with dimension. Okay. In 4 dimension, you can impose the Majorana condition.
Yes, maybe.
But you cannot impose it at the same time also the Weil condition. Yeah, impose one of them.
Yeah.
So maybe I'm still confused about how this Lagrangian you wrote down is the output of the CEICO.
Yeah.
I mean, so I presume the Lagrangian was known before the CEICO existed.
Yes.
Right, and the
Yeah,
equation of motion that you wrote down are directly from the Lagrangian.
Yes.
So in what sense does this Lagrangian follow? What is it that you know about it now that maybe you didn't know about it before?
Oh, they formulated D equals 1 and D equals 4 and equals 1 supergravity. Lagrangian was already known because the first papers on supergravity are from the 1976, and the geometric approach was introduced by Regge and Niemann in 1978. Okay, so 2 years later. On that, I cannot say anything. So the Lagrangian was already known. But so in this case, we don't know anything more.
But maybe can you just explain again, in what sense is this Lagrangian the output of your procedure?
Okay, so of course, when I wrote this, I skipped a lot of necessary steps. First, one starts with the most generic 4 form. This is 2 form, 1 form, 1 form. So one writes the most generic 4 form. Then this 4 form must be written in terms of mu's, okay, wedges, okay, these, the differential operator, and possibly 0 forms. In this case, we have no 0 forms. Okay, so this is A. Point B is requiring that every index along H, so every index in this case, every Lorentz index in this case, has to be contracted. Okay, there cannot be free indices, and there cannot be a free spin connection, and this is the case. So you start.
No free spinning.
Exactly. Yes, as well. Of course, we have bilinears and so on. Thanks. And C, this is necessary if you want to, if I remember correctly, if you want to cancel topological terms, like the R term does not scale in the same way. Okay, so in case you want that, this condition removes the topological term. So you end up with these terms. Now this is sorry an A here, a free parameter. This is fixed. Whenever we study the equations of motion, we said that we wanted the vacuum solution to be a solution. So we want the RA equals 0 to satisfy these equations. Okay, and this happens only when A equals 4. If I left A instead of R here, I would have obtained dV plus A or psi, something like this. Okay, and this is R A. Okay, so only when A, this is not correct probably. It should be like this. Be precise, probably. Only when A is equal to 4, this is the curvature, and so it vanishes when R is 0. Okay, so this condition implies that A has to be 4.
So if A is a different value, then one of the equations of motion is that this R is not,
Yeah, this term here and here as well. So this is not a solution, and you want this to be a solution because from the start we said that the Lie group, the starting Lie group was the start of the approach. So we want the deformation of this Lie group to be the dynamical theory, but the vacuum. So when everything is fixed, we want this to be a solution. This is R equals 0. This is whenever the Murray-Cartan equations hold.
Okay, so is that it?
Yes.
So,
in this case, okay.
Okay, and where's the rheonomic?
Rheonomy has to be used whenever we find equations of motion and we want to find the physical content. Okay, these are equations of motion, but these contain too much stuff. If I expand this, I would obtain this in principle, as we have discussed before. This can be expanded on V and psi. We can have more terms here. Whenever I say that the rheonomy holds, then only these will be the non-fixed terms. These will be determined in terms of this. So the only three parameters are these. And if you plug in these there, you obtain again this. So in principle, the interesting part of rheonomy and this approach is that the equations of motion, you can find them even before the Lagrangian. You don't need the Lagrangian to find the equations of motion. These are here. And these are following from the Bianchi identities and the rheonomic constraint. Indeed, there are some cases in which the construction of the Lagrangian is not possible or has not been achieved, but you have the equations of motion. For example, I can say something that I'm working on. It's a case in which you have a self-dual 3-4, okay, in 6 dimensions. Okay, and a Lagrangian is not possible, but nonetheless, there is an information in the Bianchi identities that this is true. Then this has to hold. This is an example.
Just on that point, so
Yes.
you want rheonomy to be satisfied, but once you've chosen Lagrangian, you have some fixed set of equations of motion. You can only ask whether this set of equations of motion produces
The correct
rheonomic curvatures or not.
Yes.
Okay, so if the equations produce non-rheonomic curvatures, you say that's not a good Lagrangian.
Exactly. Well,
But,
okay.
yeah.
They will do it automatically.
Well, that's what I'm trying to understand. Why do you automatically satisfy? Yeah, not quite catching exactly what you're saying.
I mean, I think
So-
it's recursive thing. Here, these are general whatever.
Yeah.
So
Here the curvatures, I mean.
here they
yeah,
are whatever they are. Okay, and indeed, at the level of Lagrangian, you cannot use the rheonomic parameterization because they only hold on shell.
Okay.
So whenever you impose this thing, you will find that whenever you use the rheonomic parameterization inside the equations of motion, you will find the same constraints that you find from the Bianchi, because they hold both. You are both on shell.
Well, let me put it this way. Say you write down Lagrangian, you obtain equations of motion.
Yes.
But then the equations of motion allow solutions that are not rheonomic. What then?
But when you say that this, for example, if I don't impose rheonomic, this allows solutions that are not rheonomic. Of course, I could put.
All right. So then I don't understand in what sense rheonomy is part of the theory.
Well, it's part of the theory, both here and in the Bianchi. So
Maybe I'm confused, right?
okay,
So
yeah,
if-
I'm trying.
I could say, look, I like general relativity as a theory of Lagrangian equation of motion, but I also like flat metrics.
You also right?
Flat metrics.
Okay.
So there are solutions to Einstein equations which are not flat. So now what do I do with this combination? I want flat metrics, but I have a theory that has solutions that are not flat. So
Yes.
you're like in a similar situation here. So what do you propose to do?
Why do you say so? Here, I don't quite understand
You're
the
talking about
equations
a
that I.
constraint that is in addition to whatever equations of motion you.
No. The constraints are exactly the equations of mine. This is what I get.
No, but I gave you an example where the constraint is much stronger than the equations of motion. Right?
Okay, so you are selecting a subset of
Yeah.
a solution.
So are you
I'm not.
You're not.
No, I'm using. I'm saying that this has to be expressed in terms of this, and
Okay.
this has to satisfy some equation. Okay, and this equation is not flat. The flat solution. These are the full Einstein equation.
Okay, but why is it that in this case, your equations of motion are compatible with this extra condition?
These equations of motion here. Okay. So you're asking why this produces this as well as this produces this.
Yeah, so did you build the Lagrangian specifically so it's compatible with?
Yes.
Knowing that in advance? Or
Yes,
first
we
do
know.
Lagrangian?
No.
And
We
check
first do this
Yeah.
and then do that.
Okay,
We are sort of guided by this. We know what we are going to get, and then we find the Lagrangian that reproduces that,
but
if it exists.
the Lagrangians, so what my question is, once you build Lagrangian, you can get the equations of motion. And then you can check compatibility with your constraint,
Yes.
right? So is that necessary, or you will know in advance that the way that you build Lagrangians will be compatible?
I have no counterexample, but of course, this doesn't mean I have no proof of this thing. I've never found a case in which this is not. There are different. Whenever you put this, of course, there. Of course, it's not. Of course, you obtain this. This is the point. It's not. Of course.
So is it a theorem? I don't know.
This is yours to figure out, right? I'm here to talk about this, right? You have to figure
But
out.
still, your claim is that every solution of these equations is rheonomic
Every solution
of the equations of motion.
with this constraint yields this. So every equation of
That's what I'm
motion with
asking.
this.
I'm asking whether all of the solutions to those equations are rheonomic.
Now, I hope that there are more solutions.
But yeah, but yes, indeed, if you don't impose this, there are many other solutions.
Okay, then I still don't understand what is the relation between the theory, this theory, given by this Lagrangian,
Okay.
this equation of motion,
This is
and
Lagrangian.
rheonomic.
This is Lagrangian.
Yeah.
You have every component here in principle. RA has RA, BC, BB, BC plus RA alpha B psi BB plus RA alpha beta psi psi. Okay, all these coefficients. If you plug in this inside this, of course you could have in principle some relation between these terms. Okay,
Following from the equation.
following from the equation. Indeed, there may be, but we are not interested in that. Physics is not interested in them because of the rheonomic constraint. So you don't want this to be free parameters, new stuff. This would mean that the information on superspace is important. There is more information than in space-time. Okay, and this is maybe true, but we have no proof of the existence of these fermionic directions in real life. So this cannot contain more. This is what Ruggero is saying. It's saying that this has to be proportional to this in some way. And indeed, when you do this, the information that you get from these equations are just you don't obtain evolutions or differential equations. You obtain algebraic constraints. So whenever you impose that these are proportional to this, you obtain only algebraic constraints from the directions here that are proportional to to psi. The only equations of motion come from the full field line sector. So this is a free form as an equation of motion. It will be expressed like in a sector V, V psi psi, psi psi V psi psi. Every sector has the values separately. So from the VVV sector, which will be the one proportional to this, you obtain the true equations of motion. From all other sectors in which these terms are expressed in terms of this, you only obtain algebraic constraints. So constraints between coefficients here in front of these terms. Does this answer?
It's still not, but maybe we could finish.
Yeah, we can
the Zoom and
postpone
then-
for
Yeah.
informal discussions. So
Okay.
thanks very much for comprehensive
Thank you.
answers.
Thank you.